Across the vast expanse of the open-pit mine, a fleet of heavy dump trucks moves in relentless formation, their steel bodies rising and lowering against terraced walls of exposed earth. Each vehicle hauls tons of loose material, ore, overburden, fractured rock, from the active excavation face to distant processing zones. In this immense landscape of dust and diesel, productivity is measured by every load delivered and every minute gained. These high-capacity haul units serve as the primary link between the extraction face and downstream processing zones, moving massive volumes of loose ore and overburden across engineered haul roads. In June 2023, construction activity at the Rogun Hydropower Plant advanced with disciplined intensity, reflecting the project's strategic importance and technical complexity. Across the vast construction zone, operations unfolded in coordinated phases, from dam body elevation works to underground powerhouse development. On the main embankment, material placement continued in controlled layers, with compaction crews methodically stabilizing each lift to meet strict geotechnical parameters. Continuous quality monitoring ensured density, moisture content, and structural integrity complied with design specifications. Simultaneously, drilling and grouting teams reinforced foundation zones, enhancing seepage control and long-term stability. Within the underground caverns, mechanical and electrical installation progressed alongside civil works. Turbine hull preparation, structural concreting, and auxiliary system integration moved forward under rigorous scheduling protocols. Heavy transport vehicles navigated designated haul routes, delivering rockfill and construction materials in a steady logistical rhythm. Slope stabilization remained a parallel priority. Excavation crews reshaped rock faces along stepped benches, while anchoring systems and protective measures were implemented to safeguard both personnel and infrastructure. Advanced surveying technologies and real-time monitoring systems supported alignment control and deformation assessment throughout the site. June marked a period of visible transformation. Elevation milestones were approached, structural volumes expanded, and the silhouette of the dam rose steadily against the mountain backdrop. The scale of coordination, engineering, logistics, safety management, and environmental oversight demonstrated a project operating at national significance. At Rogan, progress was not measured merely in cubic meters placed or meters excavated, but in the steady realization of a long-envisioned energy landmark for the region. In August, the technical inspection of construction tunnel stage 4 at the Rogun Hydropower Plant concentrated on underground structural execution and hydraulic integrity systems. This tunnel segment functions as a critical component within the water conveyance and pressure management network of the dam. Excavation works were carried out using controlled drilling and blasting methods, followed by immediate installation of primary support systems, including rock bolts, steel ribs, and shotcrete lining. Geotechnical monitoring instruments were deployed to measure deformation, stress redistribution, and groundwater ingress. Secondary lining operations involved reinforced concrete placement with high-strength mixes designed to withstand significant hydrostatic pressure. Cement grouting and consolidation injections were implemented to reduce permeability and enhance foundation bonding. Waterproof membranes and drainage galleries were integrated behind the lining to control seepage and ensure long-term durability. The tunnel's structural framework demonstrates advanced underground engineering where excavation geometry, reinforcement density, and concrete curing protocols are strictly aligned with hydrodynamic load calculations and long-term operational safety requirements. The multi-lane road tunnel project executed by China Communications Construction Company Limited represents a fully integrated underground construction operation, combining mechanized tunneling, structural prefabrication, and surface infrastructure development within a unified engineering framework. The process began with large-scale TBM assembly at the launching shaft on the east bank. Simultaneously, the slurry treatment plant was commissioned to manage excavation spoil, separating bentonite slurry from excavated soil to ensure continuous closed-loop circulation during tunneling. Segment prefabrication was conducted off-site under controlled conditions. Reinforced concrete segments underwent strict dimensional verification before entering the curing phase, where temperature and humidity were regulated to achieve optimal compressive strength. Following curing, segments were transported to site and subjected to joint inspection to confirm tolerances, gasket integrity, and embedded component alignment. Inside the tunnel, segment trains delivered precast rings directly behind the TBM shield. From the TBM control room, operators monitored thrust force, cutter head torque, slurry pressure, and alignment parameters in real time. Segment assembly was performed ring by ring within the tail shield, forming the primary lining structure immediately after excavation. The left tunnel achieved breakthrough first, marking a major milestone. Following completion, the TBM underwent precise positioning before executing a U-turn maneuver for deployment in the second tube. Trolley dismantling and system reconfiguration prepared the machine for renewed excavation. Work on the right tunnel progressed with similar technical sequencing, culminating in the breakthrough of the second tube. Internal structural works then advanced within the completed left tunnel, including in-situ concrete placement for secondary lining, roadbed slabs, and service ducts. Above ground, viaduct assembly operations proceeded in parallel, integrating elevated sections with tunnel portals. Final phases included asphalt pavement installation, completing the transition from subterranean excavation to fully operational multi-lane transport infrastructure. The Adler-Alpica service combined motorway and railway route represents one of the most complex transport infrastructure undertakings completed for the Sochi Winter Olympics. Designed to integrate a 4-lane highway with a dual-track high-speed railway, the corridor accommodates up to 6 train pairs per hour while significantly reducing travel time between the coastal hub of Adler and the mountain venues near Esto-Sadok. The system was engineered to transport approximately 20,000 passengers per hour in peak conditions. The most technically demanding segment spans 32 kilometers through the narrow Mzimta River Canyon, where elevation differences exceed 400 meters. The mountainous terrain, combined with pre-existing infrastructure corridors, imposed strict spatial limitations. Achieving high design speeds required minimizing curvature and gradients, which necessitated an extraordinary concentration of bridges and tunnels. Within this stretch alone, more than 50 kilometers of structural installations were constructed, reflecting the density of engineered solutions required. Seismic resilience was a governing design parameter. With regional seismicity rated up to magnitude 9, reinforced concrete elements were heavily strengthened, and bridge bearings incorporated energy-dissipating shock absorbers. Foundations were designed to resist both seismic acceleration and river-induced scour. Retaining walls, slope stabilization systems, sheet piling, and gabion protection were extensively applied to mitigate landslides and erosion along the riverbanks. Tunneling operations encountered heterogeneous rock formations, unstable soils, and high groundwater pressure. Up to 6 tunnel boring machines operated simultaneously, including large diameter units between 10 and 13 meters. In particularly complex zones, hybrid excavation strategies combined TBM advancement with conventional mining methods and drilling and blasting techniques. Jet grouting was widely implemented, injecting cement slurry into boreholes 12 to 50 meters deep to consolidate weak ground and stabilize tunnel crowns and portals. Bridge construction was equally intensive. 45 bridges totaling 20 kilometers were erected, including numerous structures exceeding 500 meters in length. More than 100,000 metric tons of structural steel were installed, alongside 300,000 cubic meters of concrete. The 800-meter cable-stayed bridge, featuring an 80-meter-high pylon and a 312-meter main span, became a defining structural landmark. Executed by multiple, specialized contractors under synchronized project management, the route stands as a case study in high-density infrastructure delivery under extreme geological, seismic, and topographical constraints, completed within strict Olympic timelines and to demanding performance standards. On December 31st, track laying for the 240.29-kilometer Rugin-Meju Railway officially commenced in Jiangxi Province. At the Rugin construction site, The PG-28 track-laying machine precisely positioned the first rail panels, signaling entry into a decisive construction phase. With a bridge and tunnel ratio of 73.86%, the line crosses highly complex geological formations, demanding advanced engineering control. Scheduled for core track completion in 2026, the railway will eliminate rail inaccessibility for 3 counties and significantly strengthen connectivity between southern Jiangxi and the Guangdong, Hong Kong, Macau Greater Bay Area. In sanitary sewer construction, durability depends on both structural strength and corrosion resistance. Perfect Pipe combines reinforced concrete with a fully integrated high-density polyethylene liner, creating a composite system engineered for aggressive wastewater environments. Production begins with fabrication of the HDPE liner. Sheets are cut to match the specified pipe diameter, then welded into a cylinder by certified technicians. The longitudinal seam undergoes spark testing to verify a continuous, leak-free weld. One side of the liner contains integrally formed anchors designed to embed into the concrete matrix, creating a permanent mechanical bond. The liner ends are heated and expanded, and a temporary steel ring is inserted to maintain geometry during casting. The expanded liner is positioned inside the pipe form, followed by placement of a reinforced steel cage. Spacers ensure consistent concrete cover. Self-consolidating concrete, formulated with controlled aggregates and superplasticizers, is poured to encapsulate the anchors and reinforcement without vibration. After curing under controlled conditions, the form is stripped. The temporary ring is replaced with an internal joint coupler. Dual-edge gaskets compress against the smooth liner surface, providing a watertight seal rated to 36 pounds per square inch. Standard diameters range from 24 to 60 inches, with larger configurations available. The result is a structurally robust, corrosion-resistant pipe system designed for extended service life. The Australia-Pacific Pipeline in Queensland was engineered as a high-capacity, long-distance gas transmission system extending 520 kilometers, primarily utilizing 42-inch diameter, high-pressure carbon steel pipe. Designed to transport processed coal seam gas from the Surat Basin to the LNG facility on Curtis Island, the system required strict control over welding integrity, coating performance, and hydraulic efficiency. A 40-meter construction right-of-way was established to support parallel operations, including trenching, stringing, welding, inspection, lowering in, and backfilling. 18-meter pipe joints were selected to minimize weld frequency, thereby improving productivity and reducing cumulative weld risk exposure. Automatic welding systems were deployed along a firing line configuration, achieving production rates of up to 150 girth welds per day. Each weld underwent automatic ultrasonic testing to verify internal integrity, followed by field joint preparation using grit blasting and application of multi-component liquid epoxy coatings to restore corrosion protection continuity. Trenching operations maintained a minimum burial depth of 2.25 meters to ensure mechanical protection and thermal stability. Pipe strings, pre-assembled into sections exceeding 1 kilometer, were lowered into the trench using synchronized side booms to control bending stress within allowable limits. Hydrostatic testing was conducted in sections up to 30 kilometers in length, confirming pressure containment and structural performance under operational load conditions. The completed system integrates launcher and receiver stations, scraper facilities, and mainline valve stations, forming a technically optimized high-pressure gas transmission corridor. At the Palfinger production facility in Cherven Bryeg, Bulgaria, a domestic wastewater treatment plant was implemented using the One Advanced 500 PE system by Graf. Designed to treat approximately 75 cubic meters of wastewater per day, the installation provides a reliable and fully automated solution for the production site. The construction phase began with excavation and precise leveling of the foundation to ensure uniform load distribution. A compacted base layer was prepared before positioning the large Carat XXL tanks by crane. Each tank was carefully aligned, interconnected, and secured to maintain structural stability and hydraulic efficiency. After mechanical connections were completed, the control unit was installed and calibrated. Backfilling was carried out in controlled layers to prevent deformation. The entire system, measuring about 28 meters long, was completed within 5 days and commissioned following final inspection and flow testing. In February 2017, the Oroville Dam faced one of the most severe hydraulic events in its history. Record rainfall, nearly 18 inches in just 2 months, combined with extreme snowmelt inflows, pushed the reservoir to critical levels. As water surged over the emergency spillway and damage expanded along the main spillway chute, 188,000 residents were evacuated as a precaution. The reconstruction effort that followed was one of the largest emergency dam repairs ever undertaken in the United States. Crews were tasked with demolishing and replacing more than 3,000 feet of spillway before the next rainy season. The upper section was rebuilt using roller compacted concrete as a structural foundation, topped with high-strength structural concrete. The lower spillway posed the greatest engineering challenge, a steep 4-to-1 slope requiring concrete placement across a 37-foot width with less than a quarter-inch tolerance. Traditional vibrating screeds were unsuitable on the incline. Instead, a specialized roller screed and trolley system was deployed, enabling uphill finishing without vibration, maintaining alignment, surface uniformity, and long-term structural performance under extreme hydraulic loads. By the end of 2025, roller compacted concrete placement for the gross dam raise had reached a significant structural milestone. Since 2023, the dam crest has been elevated 109 feet above the original structure, leaving approximately 22 feet to achieve the final design height of 471 feet. Placement operations averaged slightly more than 1 vertical foot per day. Concrete was delivered, spread by bulldozers equipped with GPS-grade control and compacted using vibratory rollers to achieve a uniform 1-foot lift thickness. Survey crews verified elevations after each layer to maintain strict geometric tolerances. Continuous water curing was applied to ensure proper hydration and bonding between successive lifts. Formwork systems controlled the dam geometry. The upstream face utilized 16-foot vertical panels, periodically raised as elevation increased. The downstream face advanced in 4-foot increments, stepping inward 2 feet per lift to form the design profile. Winter protection measures were installed, and interior works and stilling basin construction continued during the cold season. The Fehmarnbelt Tunnel represents one of the most technically ambitious infrastructure projects in Europe, spanning 18 kilometers between Rotbyhaven on Denmark's Lolland Island and Puttgarden in Germany. Construction began with the development of a vast production facility at Rotbyhaven. This purpose-built complex includes deep basins, a work harbor, and 3 large casting halls where tunnel elements are manufactured under controlled industrial conditions. Each standard element measures 217 meters in length, weighs more than 73,000 tons, and integrates 5 parallel passages, 2 motorway tubes, 2 railway tubes, and a central service corridor. Approximately 300 cubic meters of concrete are poured per segment, with casting lasting around 30 hours. Once cured, each 24-meter segment is advanced toward the dry dock. 9 segments are post-tensioned together to create a complete tunnel element. After casting, bulkheads seal each element watertight before the dry dock is flooded. Despite their mass, the elements float due to buoyancy. Tugboats tow them to position above the trench. Immersion is controlled from a specialized vessel, using ballast tanks to maintain precise balance. Advanced sensors guide positioning with an accuracy of up to 12 millimeters. Water is pumped from the joint, creating pressure that compresses dual rubber gaskets, ensuring long-term watertight integrity and thermal flexibility. Once installed, the trench is backfilled with gravel, sand, and protective stone layers. Technical installations for road and rail systems proceed from both national sides until the final closure element connects the 2 ends, completing a critical green transport corridor for Europe. On a cable-stayed bridge, such as the Zuari Bridge, cable installation represents one of the most technically demanding and structurally decisive phases of construction. These stay cables are not secondary components. They are the primary load-carrying elements that transfer deck forces directly into the pylons and down to the foundations. Their installation requires geometric precision, calibrated tensioning, and strict sequencing control. The process typically advances in tandem with deck segment erection. As each precast or cast-in-situ deck segment is positioned, often using balanced cantilever methodology, temporary supports stabilize the segment until its corresponding stay cable is installed and stressed. This sequencing is critical to maintain equilibrium across the span and prevent asymmetric loading on the pylons. Cable installation begins with the preparation of anchor zones within the deck and pylon. Steel anchor boxes, embedded plates, and guide pipes are aligned to millimeter tolerances. These anchor assemblies are engineered to distribute concentrated tensile forces into the surrounding reinforced concrete without inducing localized cracking or stress concentrations. Once anchor readiness is verified, individual strands or prefabricated parallel strand cables are hoisted. On large spans like the Zuari Bridge, strand-by-strand installation is often employed. High-strength galvanized steel strands are threaded through protective HDPE sheaths and guided through pylon saddles or anchor pipes using winches and synchronized lifting systems. Specialized rollers and temporary supports prevent abrasion during pulling operations. After strand placement, the stressing phase begins. Hydraulic jacks are mounted at the anchorage end, and each strand is tensioned to a predetermined force based on structural analysis models. These forces are not arbitrary. They are calculated to achieve the exact deck profile and camber required under dead load conditions. Load cells and elongation measurements verify that theoretical and actual stresses align within tight tolerances. Tensioning is executed in stages. Initial stressing stabilizes the deck segment, while subsequent fine-tuning corrects geometry as additional segments and cables are added. Survey teams continuously monitor deck elevation, pylon deflection, and cable angles using total stations and real-time instrumentation. Any deviation from predicted behavior triggers recalibration of tension values. Corrosion protection is integrated throughout the process. Each strand is factory-coated, typically with corrosion-inhibiting grease, and sheathed in polyethylene. After stressing, anchor heads are sealed, and the full cable assembly is injected or sealed to create a multi-layer protection system designed to withstand coastal environmental exposure, including humidity and chloride presence. Aerodynamic performance is another engineering consideration. External HDPE ducts may incorporate helical fillets or surface treatments to mitigate rain-wind-induced vibrations. Dampers are installed near the deck anchorage to control oscillations and ensure long-term fatigue resistance. As installation progresses symmetrically from the pylons outward, the bridge gradually transforms from a temporary cantilevered structure into a fully integrated cable-stayed system. Each installed cable redistributes internal forces, reduces bending moments in the deck, and increases global stiffness. By completion, the cable network functions as a precisely tuned structural orchestra, every strand calibrated, every anchorage secured, every geometric parameter verified. On the Zuari cable-stayed bridge, cable installation is not simply an assembly operation. It is the moment when structural theory is translated into suspended reality, and the bridge begins to carry its own weight with engineered confidence. The new cable roof at Ciutat de Valencia Stadium represents a precision-engineered upgrade designed to deliver long-span performance with minimal structural intrusion. Developed through advanced BIM-based integrated design platforms, the system optimizes geometry, load paths, and constructability before field execution. At its core is a 1,040-ton compression ring carefully shaped to balance radial forces generated by the tensioned cable network. The roof is supported by 84 slender steel columns, strategically positioned to limit intervention on the existing stadium framework. The cable system itself weighs approximately 150 tons, including connection assemblies, and works in combination with 84 compression struts, rising up to 9 meters. Installation involved lifting the lower annular cables followed by a controlled tensioning sequence to achieve final geometry and stiffness. The structure spans up to 40 meters, supporting 17,000 square meters of roof cladding and 8,000 square meters of tensile membrane. 221 BY 7-meter scoreboards are suspended directly from the cable network are the optimum solution for long-span roofs and for existing stadium upgrades with minimum disruption on events. The civil engineers behind Lowestoft's third crossing transformed Gullwing Bridge into both an infrastructure landmark and a catalyst for new talent. From precision bascule tolerances to complex span installations, the project sharpened technical expertise, inspired graduates, and left a lasting legacy of skills, collaboration, and community impact. In March 2024, the final bascule span of the Gullwing Bridge in Lowestoft was installed, marking a major structural milestone. Measuring 39.5 meters long, 22 meters wide, and 35 meters tall, the span weighs approximately 120 tons during installation, including temporary ballast for stability. A 380-ton concrete counterweight is integrated within the J-beams for commissioning. Once operational, the bridge clears the highest tide by 12 meters, with structural elements rising more than 50 meters above sea level. In professional asphalt paving, performance depends on strict control of base preparation, placement temperature, and compaction sequencing. A stable subgrade is first graded and compacted to achieve uniform bearing capacity. Any soft spots are removed and replaced to prevent future settlement. A properly designed aggregate base layer ensures structural support and promotes drainage. Hot mix asphalt must be delivered and placed within the optimal temperature range to maintain workability and bonding characteristics. Once laid, compaction begins as soon as the mat can support equipment without displacement. The rolling pattern typically progresses from breakdown rolling to intermediate and finish rolling, achieving maximum density while eliminating air voids. Edge detailing is critical. Seams, curb interfaces, and tie-ins are compacted using hand tools and plate compactors to prevent weak joints. Surface smoothness and density are continuously monitored to ensure durability, load resistance, and long-term performance. In Westminster, Colorado, the Gomaco Commander 3 4-track slipform paver is constructing the new Type 9 glare screen barrier, an advanced 56-inch high safety profile designed for enhanced vehicle separation and headlight screening. Wider and taller than the traditional 36-inch barrier, The section measures approximately 2 feet at the base and tapers to 6 inches at the top in a symmetrical configuration optimized for stability. Production spans nearly 15,000 linear feet, with daily output approaching 400 feet. Concrete control is critical. A low slump, half-inch wet batch mix ensures the barrier holds its shape as the mold advances. The glare screen incorporates 11 horizontal reinforcing bars, requiring careful staging and continuous monitoring to prevent movement during placement. Minor mold refinements have improved efficiency, reducing cleanup time and maintaining consistent surface quality. Precision alignment and disciplined finishing ultimately define the performance of this modern highway barrier system. Mobilization for the new Suez Canal dredging campaign began with a tightly sequenced marine logistics operation. The cutter suction dredger Almirfa was positioned onto a heavy lift transport vessel in a precisely coordinated 2-hour loading window. Within the next hour, designated support vessels were secured on board, followed by the boarding of the cargo and rock barge Fidela, completed in approximately 90 minutes. Once fully loaded, controlled deballasting procedures were executed over 11.5 hours to restore optimal draft and navigational stability. The transport vessel then departed from the UAE, following a calculated sailing corridor toward the Suez Canal. Upon arrival, offloading operations commenced, transitioning immediately into technical preparations before full-scale dredging activities began. Denver Water is advancing critical construction and infrastructure upgrades across its system. Lead service lines are being excavated and replaced with modern, corrosion-resistant piping. The new Northwater treatment plant near Golden features reinforced concrete structures, advanced filtration systems, and high-capacity pumping equipment. Aging water mains are replaced using both open-cut and trenchless methods to improve reliability. Structural inspections of tunnels, dams, and underground pipelines utilize robotic and sensor-based technologies to ensure long-term performance and system integrity. Jensen Infrastructure operates in the field of precast and engineered infrastructure components, expanding beyond traditional concrete systems into steel, fiberglass, and polymer-based solutions. Core technical processes include reinforced cage fabrication, controlled concrete batching, vibration consolidation, and regulated curing to achieve required compressive strength, durability, and dimensional tolerances. Manufacturing is based on standardized formwork systems and repeatable production lines to ensure quality consistency. The integration of alternative materials allows improved corrosion resistance, reduced structural weight, and enhanced performance in aggressive environments. Engineering activities involve structural design verification, load analysis, hydraulic performance assessment, and compliance with infrastructure codes and specifications. Typical applications include stormwater structures, wastewater chambers, utility vaults, transportation elements, and protective housings for electrical and communication networks. In Pacific Grove, Monterey County, crews are installing a PTS-69 intercept vault. The structure consists of a 6BY 9-foot multi-section precast tunnel vault designed to provide underground access for telecommunications infrastructure. Installation begins with precise base preparation and alignment to ensure great accuracy and load distribution. The center sections, including integrated manhole access openings, are set sequentially using crane lifting and controlled placement. Each joint is aligned and sealed to maintain structural continuity and watertight performance. The final component, referred to as the female end section, completes the vault assembly. Once positioned and connected, the system is prepared for backfilling and compaction to restore surface conditions and ensure long-term structural stability. Blowing installation is a delivery and placement method for LECA lightweight expanded clay aggregate directly from a truck to the construction site through flexible hoses. The process begins with site preparation and positioning of the truck. Hoses are laid out, connected, and attached to the truck's blower system. A water hose can be connected to reduce dust during operation. During placement, the material is blown at a rate of approximately 1 cubic meter per minute. The lightweight aggregate distributes evenly around pipes and service installations. The surface is then leveled manually. Immediate compaction of about 8 to 10% occurs during blowing. For fill depths under 40 centimeters, no additional compaction is required. For depths exceeding 40 centimeters, compaction may be performed in 1 meter layers using a plate compactor not exceeding 140 kilograms. Ryan Rude Construction completed placement of a massive 82-foot diameter grain bin foundation using the Lura Lightning Strike roller screed system. The circular slab, built to a 41-foot radius, required strict dimensional control to ensure accurate anchor bolt alignment for the steel bin structure. As the concrete is placed, the Lura Lightning Strike roller screed moves smoothly across the massive circular slab, striking off and leveling the surface with consistent control. Covering such a wide radius demands steady coordination and tight elevation checks to maintain uniform thickness and flatness. The result is a clean, precisely finished foundation built to handle heavy vertical grain loads and long-term service demands. Big diameter, tight tolerances, executed with efficiency and technical confidence. At Gullwing in Lowestoft, a purpose-built heavy transport system was deployed to maneuver the colossal bridge span, an ultra-heavy modular platform engineered to carry extreme loads with millimeter precision during final positioning. The next trencher D250 is a high-precision disc trencher attachment engineered for installation on hydraulic excavators. Designed specifically for urban utility works, the D250 excavates trenches up to 80 centimeters deep, with adjustable widths ranging from 12 to 25 centimeters, delivering controlled, dimensionally accurate cuts even in rocky ground conditions. Its disc-based excavation system produces a clean, vertical pavement cut aligned precisely with project specifications, minimizing overbreak and surface disturbance. The fully enclosed design significantly reduces debris dispersion, allowing traffic and surrounding activities to continue with minimal disruption. This containment also enhances operational safety and environmental cleanliness in dense urban environments. A hydraulic swing system enables perpendicular positioning of the cutting disc relative to the excavator, facilitating efficient installation of service connections and secondary pipelines branching from primary lines. Material removal can be configured via conveyor belt or integrated vacuum extraction. The D250 ensures productivity, trench accuracy, and long-term pipeline installation quality. As aging concrete silos begin to deteriorate due to cracking, material fatigue, and long-term exposure to moisture and environmental loads, structural strengthening becomes essential to maintain operational safety. High internal pressures from stored grain generate circumferential tensile stresses that can exceed the original design capacity over time. Rhino carbon fiber systems utilize externally bonded carbon fiber reinforced polymer to restore and enhance structural performance. The application process begins with detailed structural assessment, surface cleaning, latence removal, and crack injection repair if required. An epoxy primer is applied, followed by saturation resin and placement of carbon fiber fabric around the silo circumference in calculated wrap patterns based on engineering design. The CFRP layers act as external tensile reinforcement, increasing hoop strength and flexural capacity. Carbon fiber provides up to 10 times the tensile strength of steel while adding minimal weight and offering corrosion resistance. Installation is rapid, minimizes operational disruption, and can be applied in multiple layers depending on required load upgrades, extending service life without demolition. To ensure long-term durability and effective drainage, the improvement and construction of block paving must strictly adhere to technical requirements right from the preparation stage. Proper base preparation is critical. The bedding layer of screened aggregate must be even and well compacted, meeting the specified compaction coefficient. Cushion thickness tolerance must not exceed plus or minus 10 millimeters. Tile displacement is limited to 2 millimeters, and finished surface elevations must comply with project levels within plus 5 millimeters. The design slope, typically 10 to 20 millimeters per meter, must be maintained to ensure drainage. Vertical offsets between adjacent pavers must not exceed 3 millimeters. Compaction is performed using a plate compactor with a rubber mat to prevent surface damage. Joints, 2 to 3 millimeters wide, are filled with dry sand or specified material, thoroughly brushed to eliminate voids. Drainage channels are set on cast-in-place concrete and aligned to grade. Pipework is installed in prepared trenches using compression fittings, with accurately cut and sealed joints to prevent leakage. Rogan is entering a decisive phase of advancement, as the monumental hydropower project becomes progressively equipped with next-generation infrastructure. Along the steep slopes of Rogan, heavy drilling equipment operates across multiple elevation tiers, transforming the mountainside into a precisely engineered work zone. Rotary rigs anchor into rock faces, percussion drills, fracture-dense formations, and support machinery stabilizes each bench with calculated accuracy. This layered deployment of machinery reflects the project's scale and technical rigor, where each drilled meter advances structural reinforcement and prepares the terrain for the next phase of monumental construction.